In this lesson, you will learn about the fundamentals of FortiGate High Availability, HA, and how to configure it. FortiGate HA provides a solution for enhanced reliability and increased performance. In this lesson, you will explore the following topics: HA operation modes, HA cluster synchronization, HA failover and workload, monitoring and troubleshooting. After completing this section, you should be able to identify the different operation modes for high availability, HA, understand the primary FortiGate election in an HA cluster. By demonstrating competence in HA operation modes and primary FortiGate election, you will be able to choose and implement the right high availability, HA operation mode in your network based on your requirements. You will be able to use the FortiGate devices effectively in your network. The idea of HA is simple. HA links and synchronizes two or more devices. In FortiGate HA, one FortiGate device acts as the primary appliance, also called the active FortiGate. It synchronizes its configuration to the other devices. The other FortiGates are called secondary or standby devices. A heartbeat link between all the appliances is used to detect unresponsive devices. What is synchronized between the devices? Are all FortiGate devices processing traffic? Does HA improve availability, or does it improve throughput? The answers vary, depending on the HA mode. There are currently two HA modes available: active-active and active-passive. Let's examine the differences. First, let's take a look at active-passive mode. In either of the two HA operation modes, the configuration of the secondary FortiGates is synchronized with the configuration of the primary device. In active-passive mode, the primary FortiGate is the only FortiGate device that actively processes traffic. Secondary FortiGates remain in passive mode, monitoring the status of the primary device. If a problem is detected in the primary FortiGate, one of the secondary devices will take over the primary role. This event is called HA failover. The other HA mode is active-active. Like active-passive HA, in active-active HA, all FortiGate configurations are synchronized. Also, if a problem is detected in the primary device, one of the secondaries will take over the role of the primary to process the traffic. However, one of the main differences in the active-passive mode is that in the active-active mode, all of the FortiGate devices are processing traffic. One of the tasks of a primary FortiGate in active-active mode is to balance some of the traffic among all the secondary devices. So how do the FortiGate devices in an HA cluster communicate? FortiGate HA uses FGCP, the FortiGate clustering protocol, for HA-related communications. FGCP travels between the clustered FortiGate devices over the links that you have designated as the heartbeats. You should create a heartbeat link between two FortiGate devices using a regular RJ45 or crossover cable. If you have another device between the two FortiGates, such as a switch, ensure that it is dedicated and isolated from the rest of your network. This way, critical FGCP traffic does not need to compete with the other traffic for bandwidth. NAT mode cluster and transparent mode cluster use different Ethernet type values to discover and verify the status of other FortiGates in an operating cluster. FortiGates in a cluster use telnet sessions over TCP port 23, with Ethernet type 0x8893 over heartbeat links, to synchronize the cluster configuration and to connect to the CLI of another FortiGate in a cluster. Starting in FortiOS 5.6.0, when you manually restart or shut down the primary FortiGate, before the primary FortiGate actually shuts down, it becomes the secondary device in an HA cluster and waits for the traffic to fail over to new primary before it shuts down or reboots. FortiGate HA configuration requires a specific setup in devices. First, at least 2, but up to 4 FortiGate devices with the same firmware, hardware model and VM license, FortiGuard, FortiCloud, and FortiClient licenses, hard drive capacity and partitions, operating mode, transparent or NAT. What if one of the FortiGate devices has a lower level of licensing than other FortiGate devices in the cluster? All of the FortiGates in the cluster will revert to that lower licensing level. For example, if you only purchase FortiGuard web filtering for one of the FortiGate devices in a cluster, when the cluster is operating, none of the cluster members will support FortiGuard web filtering. Second, at least one link between the FortiGate devices for HA communication. HA communication is called heartbeat traffic. For redundancy, up to 8 heartbeat interfaces can be created. If one link fails, HA will use the next one as indicated by priority and position in the heartbeat interface list. Third, the same interfaces on each FortiGate device have to be connected to the same switch or LAN segment. Notice that in the example shown on the slide, the FortiGate devices are redundant to mitigate failure. But the switches and their links still are a single point of failure. As we will see later, you can also have redundancy in the network switches and links. As a best practice and Fortinet recommendation, configure the FortiGate interfaces with static IP addresses when forming an HA cluster. Once an HA is formed, you can configure the DHCP or PPPoE addressing for an interface. If an interface is configured for DHCP or PPPoE, enabling HA may result in the interface receiving an incorrect address, or not being able to connect to the DHCP or PPPoE server correctly. The process for electing the primary FortiGate depends on an HA setting called HA override. This slide shows the process and selection criteria that a cluster uses to elect the primary FortiGate when the HA override setting is disabled, which is the default behavior. Note: the selection process stops at the first matching criteria that successfully selects a primary FortiGate in a cluster. 1. The cluster first compares the number of monitored interfaces whose statuses are up. The FortiGate device with the most available monitored interfaces becomes the primary. 2. The cluster compares the HA uptimes of the individual devices. If the HA uptime of a device is at least 5 minutes more than the HA uptimes of the other FortiGates, it becomes the primary. 3. The FortiGate with the configured highest priority becomes the primary. 4. The cluster chooses the primary by comparing the serial numbers. When HA override is disabled, the HA uptime has precedence over the priority setting. If for any reason you need to change which device is the current primary, you can manually force a failover event. When the override setting is disabled, the easiest way of doing this is by executing the CLI command diagnose sys HA reset-uptime in the primary FortiGate. Note: the reset-uptime command resets the HA uptime internally and does not affect the system uptime displayed on the dashboard of a FortiGate. Also, if a monitored interface fails or a FortiGate in a cluster reboots, the HA uptime for that FortiGate is reset to 0. Note: you can view the HA uptime difference between the cluster members. The device with 0 in the uptime column indicates the device with lower uptime. In this example, the device ending with serial number 92 has an HA uptime 7,814 over 10 seconds greater than the other device in the HA cluster. The reset_CNT column indicates the number of times HA uptime has been reset for that device. You can alter the order of the selection criteria that clusters consider when electing the primary FortiGate. If the HA override setting is enabled, priority is considered before the HA uptime. The advantage of this method is that you can specify which device is the preferred primary every time, as long as it is up and running, by configuring it with the highest HA priority value. The disadvantage is that a failover event is triggered not only when the primary fails, but also when the primary is available again. When a primary becomes available again, it takes back its primary role from the secondary FortiGate that temporarily replaced it. Note: the selection process stops at the first matching criteria that successfully selects a primary FortiGate in a cluster. When override is enabled, the easiest way of triggering a failover is to change the HA priorities. For example, you can either increase the priority in one of the secondaries or decrease the priority in the primary. The override setting and device priority values are not synchronized to all cluster members. You must enable override and adjust device priority manually and separately for each cluster member. Good job! You now understand HA operation modes and the election of the primary FortiGate in an HA cluster. Next, you'll learn about HA cluster synchronization. After completing this section, you should be able to identify primary and secondary device tasks in an HA cluster, identify what is synchronized between HA cluster members, configure session synchronization for seamless failover. By demonstrating competence in cluster synchronization, you will be able to identify the tasks of FortiGate devices and what is synchronized between the cluster members. You will also learn how to configure and use session synchronization for specific types of traffic for seamless failover. So, what are the tasks of a primary FortiGate? It monitors the cluster by sending hello signals and listening for replies to determine if other FortiGate devices are alive and available. It also synchronizes its routing table, DHCP information, and part of its configuration to the other devices. Optionally, you can configure the primary FortiGate to synchronize some of the traffic session information to all of the secondary devices. This allows a faster, seamless failover for some sessions. Some applications will not need to re-establish their sessions after a failure of a primary FortiGate. We will discuss which session information can be synchronized later in the lesson. In active mode only, a primary FortiGate also distributes certain traffic among all the available devices in the cluster. Now, let's take a look at the tasks of secondary FortiGates. If the mode is active-passive, the secondaries simply wait, receiving synchronization data but not actually processing any traffic. If the primary FortiGate fails, the secondaries will elect a new primary. In active mode, the secondaries don't wait passively. They process all traffic assigned to them by the primary device. What about the heartbeat interfaces? You don't need to configure heartbeat interfaces. FortiGate Clustering Protocol automatically negotiates the heartbeat IP addresses based on each device's serial number. The IP address 169.254.0.1 is assigned to the device with the highest serial number. The IP address 169.254.0.2 is assigned to the device with the second highest serial number, and so on. The IP address assignment does not change when a failover happens. Regardless of the device role at any time, primary or secondary, its heartbeat virtual IP address remains the same. A change in the heartbeat IP addresses might happen when a FortiGate device joins or leaves the cluster. In those cases, the cluster renegotiates the heartbeat IP address assignment, this time taking into account the serial number of any new device, or removing the serial number of any device that left the cluster. The HA cluster uses these virtual IP addresses to distinguish the cluster members and update configuration changes to the cluster members. There are a few items that need to be considered when connecting heartbeat interfaces and configuring interface monitoring. Heartbeat ports contain sensitive information about cluster configuration and require a fair amount of bandwidth to make sure cluster configurations are in a synchronized state at all times. You must have at least one port for the heartbeat traffic, preferably two. As a best practice, configure an alias for the heartbeat interfaces. It helps to identify what these interfaces are being used for in an HA cluster. Note: heartbeat communication can be enabled for physical interfaces, but not for VLAN subinterfaces, IPsec VPN interfaces, redundant interfaces, 802.3AD aggregate interfaces, or FortiGate switch ports. You should configure interface monitoring only for those ports whose failure should trigger a device failover. For example, high-priority traffic ports. You should not configure port monitoring for dedicated heartbeat ports. As a best practice, wait until a cluster is up and running and all interfaces are connected before enabling interface monitoring. A monitored interface can easily become disconnected during initial setup and cause failovers to occur before the cluster is fully configured and tested. To prepare for a failover, an HA cluster keeps its configurations in sync. Let's take a look at that now. FortiGate HA uses a combination of both incremental and complete synchronizations. When a new FortiGate is added to the cluster, the primary FortiGate compares its configuration checksum with the new secondary FortiGate configuration checksum. If the checksums don't match, the primary FortiGate uploads its complete configuration to the secondary FortiGate. After the initial synchronization is complete, the primary will send any further configuration changes done by an administrator to all the secondaries. For example, if you create a firewall address object, the primary doesn't resend its complete configuration. It sends just the new object. HA propagates more than just configuration details. Some runtime data, such as DHCP leases and routing tables, are also synchronized. By default, the cluster checks every 60 seconds to ensure that all devices are synchronized. If any secondary is out of sync, the checksum of secondary devices is then checked every 15 seconds. If checksums don't match for 5 consecutive checks, a complete resynchronization is done. Not all the configuration settings are synchronized. There are a few that are not, such as the system interface settings of the HA reserved management interface and the HA default route for the reserved management interface, in-band HA management interface, HA override, HA device priority, the virtual cluster priority, the FortiGate host name, the HA priority setting for a ping server or dead gateway detection configuration, licenses, caches. The primary FortiGate synchronizes all other configuration settings, including other configurations related to HA settings. Session synchronization enables seamless failover for some traffic. The information of some sessions is synchronized, so when the primary fails, the new primary can take over those sessions where they were left and keep them open. Traffic might be interrupted for a few seconds, but the network applications don't need to reconnect the sessions again. Once session synchronization is enabled, the device synchronizes TCP and IPsec VPN sessions that comply with one requirement. They are not handled by proxy-based security profiles. Although, session using flow-based security profiles is supported, but failed-over sessions are no longer inspected by security profile functions. Note: if both flow-based and proxy-based security profile features are applied to a TCP session, that session will not resume after a failover. You can optionally enable the synchronization of UDP and ICMP sessions. Although both protocols are sessionless, entries are created in the FortiGate session table for each UDP and ICMP traffic flow. Usually, this synchronization is not required, because most of the network applications based on UDP or ICMP are able to keep the communication even when their session information is lost. You can also enable synchronization of multicast sessions. The multicast time to live (TTL) timer controls how long to keep synchronized multicast routes on the secondary devices in an HA cluster, so they are present on the secondary devices when it becomes the new primary device after a failover. The synchronization of SSL VPN sessions is not supported. Good job! You now understand HA cluster synchronization. Next, you'll learn about HA cluster failover protection types and workload for primary and secondary FortiGates in an HA cluster. After completing this section, you should be able to identify the HA failover types, interpret how an HA cluster in active-active mode distributes traffic, implement virtual clustering per virtual domain (VDOM) in an HA cluster. By demonstrating competence in failover types and workload, you will be able to identify how enhanced reliability is achieved through HA failover protection. You will also learn about distribution of traffic in active-active cluster and distributing traffic using virtual clustering. The most common types of failovers are device failovers and link failovers. A device failover is basically triggered when the primary FortiGate stops sending heartbeat traffic. When this happens, the secondaries renegotiate a new primary. A link failover occurs when the link status of a monitored interface on the primary FortiGate goes down. You can configure an HA cluster to monitor the link status of some interfaces. If a monitored interface on the primary FortiGate is unplugged or its link status goes down, a new primary FortiGate is elected. If session pickup is enabled for the type of traffic you want to synchronize among cluster members, the sessions are resumed in the event of device failover or link failover. There are multiple events that might trigger an HA failover, such as hardware or software failure in the primary FortiGate, or an issue in one of the primary's interfaces. When a failover occurs, an event log is generated. Optionally, the device can also generate a SNMP trap and an alert email. To forward traffic correctly, a FortiGate HA solution uses virtual MAC addresses. When a primary joins an HA cluster, each interface is assigned a virtual MAC address. The HA group ID is used in the creation of virtual MAC addresses assigned to each interface. So, if you have two or more HA clusters in the same broadcast domain and using the same HA group ID, you might get MAC address conflicts. For those cases, it is strongly recommended to assign different HA group IDs to each cluster. Through the heartbeats, the primary informs all secondaries about the assigned virtual MAC address. Upon failover, a secondary adopts the same virtual MAC addresses for the equivalent interfaces. The new primary broadcasts gratuitous ARP packets, notifying the network that each virtual MAC address is now reachable through a different switch port. Note: the MAC address of a reserved HA management interface is not changed to a virtual MAC address. Instead, the reserved management interface keeps its original MAC address. As you learned earlier in this lesson, if a primary fails, a new primary is elected. But what happens if a secondary FortiGate device fails? It depends on the HA mode. In an active-passive cluster, the primary only updates its list of available secondary FortiGates. It also starts monitoring for the failed secondary, waiting for it to come online again. However, in an active-active cluster, all secondaries are handling traffic. So the primary, which tracks and assigns sessions to each secondary, must not only update its list of available secondary FortiGates, it must also reassign sessions from the failed FortiGate device to a different secondary FortiGate. This is how the workload is distributed between roles, depending on the HA mode. Notice that traffic workload is not distributed in active-passive mode, but it is in active-active mode. Let's look at how an HA cluster in active-active mode distributes traffic. First, the client side sends a SYN packet. It's always forwarded to the primary FortiGate using the internal interface's virtual MAC address as the destination. If the primary decides that the session is going to be inspected by a secondary, the primary forwards the SYN packet to the secondary that will do the inspections. In this example, the source MAC address of the forwarded frame is changed to the physical MAC address of the primary FortiGate internal interface, and the destination MAC address is the physical MAC address of the secondary FortiGate internal interface. The secondary FortiGate starts the connection with the server by directly sending a SYN packet using the external interface physical MAC address. The secondary also responds with SYNAC to the client, for which the source MAC address is the physical MAC address of the secondary FortiGate internal interface. Next, the client acknowledges the acknowledge. It's forwarded again to the primary FortiGate using the virtual MAC address of internal interface as the destination. The primary device forwards the packet to the secondary inspecting that session, using the secondary's physical MAC address. When the server responds to the TCP SYN, again, the packet is sent to the primary using the external interface's virtual MAC address. So, the primary signals the secondary. The secondary replies to the server. The idea is not to load balance bandwidth. The traffic is always sent to the primary first. The main objective is to share CPU and memory among multiple FortiGates for traffic inspection. So far, we've discussed HA clustering, where each FortiGate device acts as a whole security domain. But if you have an HA cluster with multiple VDOMS, you can configure virtual clusters. Virtual clusters allow you to have one device acting as the primary for one VDOM and as the secondary for a different VDOM. Each VDOM has a primary and a secondary FortiGate, and any device can act as the primary for some VDOMs and as the secondary for the other VDOMs at the same time. Because traffic from different VDOMs can go to different primary FortiGates, you can use virtual clustering to manually distribute your traffic between the two cluster devices and allow the failover mechanism for each VDOM between two FortiGates. Note: you can configure virtual clustering between only two FortiGate devices with multiple VDOMs. At the beginning of this lesson, you reviewed a simple HA topology. Now, let's look at a more robust topology. It is called full mesh HA. The idea is to prevent any single point of failure, not only in the FortiGate devices, but also in the network switches and interfaces. As you can see on this slide, you have two FortiGates for redundancy, and each FortiGate is connected to two redundant switches using two different interfaces. A full mesh HA is more complicated to assemble and administer, but it can provide the availability required by critical installations. This solution is only available with higher-end FortiGate models because not all FortiGate models are capable of creating aggregated or redundant interfaces, which are required for building this type of topology. Good job! You now understand HA failover and workload. Next, you'll learn about monitoring and troubleshooting an HA cluster. After completing this section, you should be able to verify the normal operation of an HA cluster, Configure HA management interface. Upgrade an HA cluster's firmware. By demonstrating competence in monitoring and troubleshooting, you will be able to make sure cluster is synchronized properly. You will also learn how to configure and access secondary devices in an HA cluster and how to upgrade the firmware on the HA cluster. If the HA cluster has formed successfully, the GUI displays all the FortiGate devices in the cluster. It shows cluster members' synchronized status, host names, serial numbers, roles, priorities, uptime, and active sessions. You can view the HA status by adding HA Status Dashboard widget. You can also view HA status information by clicking System, HA, where you can see more details by adding columns such as checksum, CPU, and memory, to name a few. You can also disconnect a cluster member from the cluster and edit the HA configurations. You can get more information about the status of the HA from the CLI. For example, the command diagnose sys HA status displays heartbeat traffic statistics, as well as the serial number and HA priority of each FortiGate. This command also shows the heartbeat interface IP address automatically assigned to the FortiGate with the highest serial number. Remember, the heartbeat IP address assignment changes only when a FortiGate leaves or joins the cluster. Another indication of the health of an HA cluster is the status of the configuration synchronization. The diagnose sys HA checksum command tree provides many options that you can use to check or recalculate the HA checksum. To check that all the secondary configurations are synchronized with the primary configuration, execute the diagnose sys HA checksum cluster command to view the checksums of all cluster members from any FortiGate in a cluster. The diagnose sys HA checksum show command shows the checksum of the individual FortiGate from which this command is executed. You can also run the diagnose sys HA checksum recalculate command from any cluster member to recalculate the HA checksums. If a secondary FortiGate displays exactly the same sequence of numbers as the primary, its configuration is well synchronized with the primary FortiGate in the cluster. In this example, the diagnose sys HA checksum cluster command is executed to view the checksums of all cluster members. Global represents the checksum of the global configuration, such as administrators, admin profiles, global logging settings, and FortiGuard settings, to name a few. Root is the checksum for the root VDOM. If you have configured multiple VDOMs, you will see checksums of all configured VDOMs. All is the checksum of the global configuration, plus all the VDOMs checksums. When troubleshooting a problem in an HA cluster, it is useful to know that you can connect to the CLI of any secondary FortiGate from the CLI of the primary FortiGate. You have to use the command execute HA manage with the secondary HA index for that purpose. To get the list of secondary FortiGates with their HA indexes, you can add a question mark to the end of the execute HA manage command. Execute HA manage question mark. If you want to be able to connect to each device directly, you can reserve an interface for HA management. The FGCP cluster supports reserved HA management interfaces in both NAT and transparent mode. You can configure up to 4 dedicated management interfaces. The configuration of a reserved HA management interface is not synchronized between HA cluster members, and each device can have different management IP addresses. The HA reserved management interface can also be used by each device to send SNMP traffic and logs independently. What if you don't have a free interface available to reserve it as a dedicated HA management interface? You can configure a management IP address from the CLI on any interface that is connected to a network and processing traffic. This doesn't require reserving an interface just for management access, and is an alternative to reserving a dedicated HA management interface. As with a standalone device, when upgrading an HA cluster, each updating FortiGate device must reboot. As the uninterruptible upgrade is enabled by default, the cluster upgrades the secondary FortiGates first. Once all the secondary FortiGates are running the new firmware, a new primary is elected and the firmware in the original primary device is upgraded. If the cluster is operating in active-active mode, traffic load balancing is temporarily disabled while all devices are upgrading their firmware. You can change the firmware upgrade process by disabling uninterruptible upgrade from the CLI using config, system, HA. This will result in all FortiGates in a cluster being upgraded at the same time. This takes less time but interrupts the traffic flow. Congratulations! You have completed the lesson. Now, you will review the objectives that you covered in this lesson. This lesson covered the following objectives. Identify the different operation modes for HA. Understand the primary FortiGate election in an HA cluster. Identify primary and secondary device tasks in an HA cluster. Identify what is synchronized between HA cluster members. Configure session synchronization for seamless failover. Identify the HA failover types. Interpret how an HA cluster in active-active mode distributes traffic. Implement virtual clustering per VDOM in an HA cluster. Verify the normal operation of an HA cluster. Configure the HA management interface. Upgrade an HA cluster's firmware.